Alright, today's tutorial questions for week 3. We have 3 questions to go over. One regarding specific volume and density. The other 2 questions are looking at steam table questions. Alright, so let's have a look at this specific volume example. Here's quite a simple example. We have a simple rigid container containing water. When we say water in thermodynamics, we could be implying that it contains water vapor or water liquid. We're not exactly sure, and we don't really need to know at this point in time anyway. So here, what we're trying to do is actually compute the average specific volume and average density over that volume. So the question's easily solved. Density, we know, is kilograms per meters cubed. Specific volume is the inverse of the density. They're basically the same thing, but in thermodynamics we prefer to deal with specific volume rather than density. So let's go ahead. The density is just a mass divided by volume, and we can work out the density pretty easily. That's 5 kilograms spread out over that 2 cubic meters. That gives us a density of 2.5. The inverse, specific volume, is just 1 on that, which is 0.4. Pay attention to the units. Alright, on to our second example. We're using superheated steam tables to look up some properties for a fluid. In this example, we have a rigid container with volume 2 meters cubed containing 5 kilograms of water. We know the pressure is 1 megapascal, and then we need to find the temperature. We have 2 properties. We need 2 properties to find any of those things. We've got P, which is 1 megapascal, 1000 kilopascals, and we need to compute V. We did compute V in the previous example at 0.4 meters cubed per kilogram. We know this is superheated because when you look in the saturated water tables at 1 megapascal, we can see this value is larger than the saturated vapor value, so we must have a superheated vapor. So we look into our superheated vapor tables, and we can see that if you look at 1 megapascal there, we've got a whole range of specific volumes at different temperatures. Our goal is to determine what temperature our gas is at. So our mission is quite simple. We need to find where on that list our 0.4 meters cubed per kilogram is. We can see that it must fall between 500 and 600 degrees C, because the specific volume at 500 degrees C is 0.35, and the specific volume at 600 degrees C is about 0.4. So we know our temperature must be between these because our V is between these. So we need to perform a simple interpolation. We know that our value 0.4 is going to lie somewhere between 3.5 and 4, where x represents the fraction along the distance that is. So we can solve for x quite simply. It's 0.97, which means that, quite simply, 0.4 is much closer to 0.401 at 600 degrees C than it is to 500. So we know that that x represents the fraction between 500 and 600 K, which means that we can use it directly to compute the temperature, which is just 500 plus x times 100 K, which is the temperature difference between those two bands, and that gives us 597 K. And now on to our final example for this week, simple gas-liquid mixture example, and using the steam tables to collect data on that mixture. Here again we have a container containing 2 cubic meters with 5 kilograms of steam or water at 300 kPa. Assuming we have a fluid vapor mixture, that's a big clue there, determine the quality and the mass of the saturated liquid in the container. So what we want to do is actually compute how much of the steam in that box is actually a liquid, since we know it's a mixture. So we need 2 important pieces of information to help us solve this problem. We've got the pressure, which is 300 kPa. Again, we can use specific volume as our second data source, and again the specific volume is 0.4 meters cubed per kilogram. So we need to look up our saturated water pressure entry tables. We're looking for 300 kPa, and straight away we can check to make sure that our answer is going to exist on that line. By going to 300 kPa, we can see that our value, 0.4 meters cubed per kilogram, lies between the saturated vapor specific volume and the saturated liquid saturated volume. So we know that we must have a mixture here. There are 2 values. We know that our value is going to lie between Vf and Vg, so we need to solve for quality. Quality is computed using the formula I've shown there, V equals Vf plus X Vfg. X is our quality we need to solve for. You can see that that value Vfg on the table is very useful. It means we don't have to compute Vg, take away Vf manually, and that computes out to be about 0.65. Now we've got our quality, we know that the quality is the ratio of the mass of the vapor to the total mass, which means that now we can compute the mass of the vapor and the mass of the liquid. We know the total mass is 5 kilograms, and therefore we know the mass of the liquid is going to be 1 minus x times the total mass. Our x is 0.65, so 1 take away 0.65 times 5 gives us the mass of the liquid, which is 1.7. So we can see we've got 1.7 kilograms of liquid in this 2 cubic meter container, and all of the rest is vapor. If you have any questions about this tutorial, please come see me in room 714. You can email me at any time, or you can just say hello in class. Good luck, and I'll see you then.